Okay, this is then the next module of process optimization. So in this session, we'll discuss about how to define the optimization problem and then how to formulate the problem. Again, I've shown you this earlier. So course outcome and the content. So we'll discuss about the model and how to define a model, formulating the optimization problem, and then we'll talk a little bit on degrees of freedom, which I think you should have known this by now. A model is a simplified representation of reality, so it is not the same as in reality because it is only a simplified version of it. And the use of the model is that we use it so that we can understand the reality, so we can see, we have a glimpse on how one variable affects the other variables. So you can see some of the models. So a model for the clothing, and then model for the train station, model for the like housing and town, and so we have like a model for chemical components or chemical bonds. Some other mathematical models, which also includes, like, this is more like a neural network. We have inputs coming in, we have some layers and hidden layers, and then we have the output, where we will try to predict what the output would be by having this different input. And we have also some mathematical model, and then here we have also like a regression model. So if we know what our value in the x-axis, we can roughly predict what would then the value be on the y-axis, with some errors, of course. We have discussed this in the previous slide. So this is also a kind of model for the pumping power, and this is also a model for the capital cost, and this total cost is our model for the total cost. So we could see this as a model, and the same goes with the boiler model. So I put together all of these like phrase. So all models are wrong because all of them are simplifications, but some of these models, which can be they can be useful to understand the reality. And in making the model, we have to make sure that the data that we use is right, or has to make sense. So in making the model, we have the idiom of if we put the wrong data point, which means we put the garbage in, what we have from the model will then be a wrong result, which is the garbage out. So Albert Einstein once said, make everything simple but not simple enough, because if we have a very simple model, it cannot catch, or it doesn't represent the reality so much so that we can understand it. And I put my phrase on it. So a model, any model that we make, really depends on the quality of ourselves itself. Yeah, so a model can only be as good as the modeler. In the model, we have variables, and in the variables, we have like three different types of variables. One is then the continuous variables. So we could see this in the process plan, like pressure, temperature, flow rate. Yeah, these three main types of continuous variables, where we have like 0 flow rate, 0.1, 0.2, 0.3, and so on until 1, even 10 or 100 tons per hour of flow rate. Another types of variables is the discrete variable. So this takes a form of how many reactors are we going to have, how many columns, and then how many trays, how many heat exchangers. So we can say like we need to have like 1 or 2 reactors, or 3 or 4 or 5 heat exchangers. We will not be able to have like a 2.5 heat exchanger or 3.2 reactors. It's a no-go. The last type of variable is binary variables. It's about either this equipment exists or not. Are we going to have a membrane or no? Are we going to have membrane or distillation column, absorption column, or ion exchange? Those things. So it's either the equipment or the process is there, or it's not there. So if the variable of that equipment is there, that means the variable takes the value of 1. If the equipment is not present, the corresponding variable will take the value of 0. Um, we go back to our big simple example on the plants, the over example of plants. So if we see in the objective functions, like we discussed last time, so objective function is then to maximize the amount of money that we will get, which takes into account how much product that we're going to sell, how much raw materials, other resources, and then byproducts and wastes that we're going to buy or trade, and then how big is the plant that we have to invest in. So all of these are part of the variables that we take into a big equations of objective functions. Um, it is also, we could also say that it is to find what are then the design and operating variables, like how big is the plant is, how big the reactor is, what is the length of the line, to how big the pump is, and also the operating variables. Are we going to operate these columns at 20 bars or 2 bars, or like cryogenic, or 200 bars for the reactors? Yeah, that yield the optimal value or the maximum value of the objective function, which is in this case we want to maximize the amount of product. So we need to find this design, which includes the capex, and operating variables, which includes all of these opex, the raw materials, other resources, and byproducts. So if we try to um, simplify this down into some form, we have the objective functions. For example, maximizing the profit, or minimize the cost or resources. Yeah, you could choose either one. Or you could also say maximizing the NPV, for example, which you take all into account all of the profit, and then the operating costs, and then license and capex, and so on and so forth. And in it we have some constraints which we call equality constraints. So these normally like involving design variables. So for example, the conversion is related to the how much the amount of catalyst that we have in our reactor. That defines also the size of the reactor. So these are all like equations, yeah, so that involve the design variables, like what are then the operating conditions to have a certain flow rate in the distillate. And that means we have to be able to design or make some correlations between the this data with the size of the column, size of the reboilers. And apart from that, we could also have like some inequality constraints in this case. So we could operate this reactor from say 200 bar until 250 bars, for example, or a temperature of 50 degrees C to 60 or 70 degrees C. So where we can play around within this range. Yeah, so this inequality constraints is mostly they involve operating variables. So the objective functions, equality constraints, and inequality constraints, these form the optimization problem. While all of these constraints, equality and inequality constraints, these are then the models that we are going to develop before we can optimize the objective function. In mathematical terms, we have the fx as the objective function, which we want to minimize or maximize. And equality constraint is normally depicted as hx equals to 0. So we will have many h here. And then inequality constraints, we normally have like gx larger than or equal to 0, or gx lower than or equals to 0. And in many textbooks, or by default, optimization problem will then be about minimizing. We have equality constraint, and we have less than or equals to 0. So this is done by default. And the whole approach on optimization, as you will see later on, is based on this standard form of the optimization problem. So I will repeat, the standard form of optimization problem is about minimizing objective functions. So if you find yourself in maximizing positions, that means you have to multiply all of the equations in the objective functions with -1. So you will then minimize the minus of that maximization problem. And we have equality constraints, and we have to and we have like less than or equal to 0 as the inequality constraints. So this is then the standard optimization problem. X in this case assumed to be a set of continuous variables. Later on we will see if we have like a binary or integer variables, which we normally symbolize them as y. If the optimization objective functions inequality constraint, equality constraints, if they are all linear, then the whole problem will be called like linear programming problem, or LP. If any of these 1 to 3 is nonlinear, and then the whole problem will become nonlinear programming problem. And if some of the variables are integer, and it's either mixed integer linear programming or mixed integer nonlinear programming. So this is how we define either one problem is linear, the other problem is nonlinear, or it's also mixed integer linear or mixed integer nonlinear programming problem. If you put all of this into like if we imagine like a 3D, so you can imagine like we have variable x1, we have variable x2, and then the objective functions, you can see it's either moving towards you or inside of the screen, so like a 3D. We have, for example, a positive x1 variable, so that means this area over here, and this whole area is not going to be a visible area. So the visible area of x1 will then be from here on there. While the for x2 we also need to have only like positive variable of x2, for example. So this area is not going to be applicable, the negative x2. So our visible area for the x2 will then be positive x2. So now our area is about this size, yeah, the visible area. And now say for example we have one nonlinear inequality constraint, like this line over here, and then this part is not visible, and this is then the visible part. That means our visible region is now getting smaller. And if we have another nonlinear inequality constraint where this is not visible, that means this area is then the visible region. So our visible region is getting smaller and smaller. Yeah? And if we happen to have one linear equality constraint in this case, so this then one line. Yeah? So that means the visible region for our objective function is only around these equality constraints. Why? Because we have to fulfill the equality constraint. So x, the relationship between x1 and x2 has to fall on the curve. Yeah, so the objective functions, if we want to say we want to maximize it, so we have to find the value of x1 and x2 in such a way that the functions of objective function is maximized only on this line. Yeah, so having more and more constraints, you can imagine that we have less and less visible, smaller and smaller visible region, and then less a lower range of or smaller range of visible variables. So I would see this as well. Object optimization is more like if we are like a blind person, and then we don't know we are now in a quest of finding an optimum point or the optimum point. If you can see, this is a picture of Himalaya mountain, where this is then the Mount Everest, where we can say that this is then the maximum point. But say that we start somewhere here, and we are blind, and the only thing that we know is then the altitude, and then the like imagine that we are blind, so then we have the only thing that we know is then where we can go, like we are moving forward, yeah, or moving to the left or to the right, yeah, or even backwards, we don't know. since we are blind. So this is then the first thing that we know. We can move in all directions. Yeah, number one. And then number two is then we can sense either we are moving upwards or moving downwards. For example, if we have like one step forwards, we can sense if we are now like I don't know, like 5 centimeters higher than we were before, or we are going to drop down to a hill where we are going to be lower by some meters when compared to where we were before. So the whole algorithms of optimizations is about how big is the step, right? You could also have like one step, or you could also like jump from here to there. It could also be the case. Yeah. That is one. How big is then the step? Number two is then where are you going to put your step? For example, you are moving forward or to the right or to the left. So the whole algorithm is about having these two, putting these two information together. So how big is then your step, and then where to go. So you could also see here, if you see that this valley, yeah, if you are blind and then you are moving towards this line, and then you end up in this valley, and then everywhere you go, if you're moving this way or that way, you can say you can only feel that you are not getting any improvement in finding the highest positions. Since we are blind, we don't know if this is an optimum value, or if this is then a maximum point, or this is then the minimum point. What we know is that we are not changing our altitude. This is where we could say that the algorithm is stuck. And in one algorithm, it could also put you here, yeah, at this point, for example. And then if you move in that directions, it will tell you that we are now descending. So since we want to find a maximum point, we're not going to move further in these directions. And then if you move further in that directions, we also know that we are also descending, so we're not going to move further into that directions. So if we are at this point, everywhere we go, we will feel that we will be descending. So with that information, we could think that we are at an optimum point. But is this the true maximum point? Yeah, if we open our eyes, we see that this is not the true. But since we are blind, we don't know if this is then the true maximum point. So that is also the case. So complications in these objective functions, it will be impossible for us to be able to know, are we going to be in the true maximum point, or the global maximum point in this case, or like local minimum maximum point. So we have so we can see that this is then the global maximum point, this is then the local maximum over here, local maximum over there, local maximum over here. So there are many local maximum, yeah, which we will know, which we will not know. So I think this picture depicts the reality of optimization problem, which you will then encounter later on. So now, how to develop and solve models? Yeah, I put this experience based because this is my experience in how to develop and solve models. Number one, first and foremost, we have to understand the process at hand. What are we going to do, and how the process looks like? What are the variables roughly that we think is influencing the objective function? And then number two is then determine the objective function. What do we want to do? Like want to maximize profit, minimize resources, or minimize waste, or minimize the total expenditure. And then once we have the objective functions, here we put all of these objective functions together. And then from these objective functions, we have the variables. We can see the variables, and then from this we can also break down these objective functions into variables that we can fine tune, like or parameters that we can then specify. For example, the parameters is like I want to have like for example, like ambient temperature, ambient pressure, or the variables in this case like the operating conditions or the length of the reactor. And then to break down every element in the objective functions, we could use also like mind maps to aid us. I'll show later on in the example that follows. And then once we have the models, we have to check then if the model makes sense. It has to follow the mass and energy conservation law. It has to follow the transport phenomena. So it has to follow also the thermodynamic laws. Yeah, and then once we make the model, we then can see whether this model is linear programming or non-linear programming or mixed integer non-linear programming, and then we can then apply suitable optimization technique to solve the problems. And then once we solve it, we have to check and examine the sensitivity of the results. Maybe we need to find different variables or different numbers of parameters and so on and so forth. For example, so we have a heat exchanger. So we have a stream coming in. So coming in this direction, and then coming into this direction. So two streams, counter current. So the temperature here, inlet here is 170 degrees C, and we want to cool it down to 80 degrees C. The flow rate is about 500 kilogram per hour, and then the specific flow rate, which is assumed to be constant here, is 1 kilojoule per kilogram degree C. This stream is going to be cooled down by like a water stream, like cooling water. So we have the supply temperature of 25 degrees C. The heat capacity of the water is 4.2 kilojoule per kilogram degree C. But what we don't know is we don't know how much the liquid flow rate that we need to have, and then what is then the outlet temperature of the water. Yeah, and the heat will be exchanged in this counter current heat exchanger. We have U of like 1000 in this case. Just take 1000 watt per meter square degree C as the overall heat transfer coefficient for that heat exchanger. Assumed to be fixed, and then R is annualization factor. So if we want to pay the water, so we have like C as the unit cost of water. Yeah, so if we have like 1 ton per hour of flow rate, and then this 1 ton per hour will have to be calculated, we'll multiply with the C to get the like dollar or ringgit per hour or per year. And we have the capital cost of the heat exchanger as a constant A, and then multiplied by the area of the heat exchanger to the power of 0.84. And yeah, we have this some subscript and superscript which you can read. So the objective is then to design a minimum cost of the cooling system. So this cooling system, that includes the heat exchanger cost, the size of the heat exchanger, also the amount of fresh water, this amount of fresh water. We have another assumption. It is a counter current with a delta T min of 10 degrees C. So the temperature difference between the inlet and outlet of hot stream and cold stream should not be lower than 10 degrees C to facilitate the feasible thermodynamic difference for the heat to be exchanged. So your problem, the goal, the task is please write down the objective functions, some constraints, either it's equality or inequality, and then the variables involved. So before we move on, I think you should pause this video and then try to make the model or develop the model on your own. So based on the problem, we have minimization. We want to minimize the cost. Because the cost consists of we have the information on the heat exchanger cost, and we have the information on the cooling water cost. So both are the costs. So our goal is obviously to minimize the cost. So we can just sum this together. So exchanger cost, cooling water cost, and then we have the first constraint is then the amount of heat transferred from the hot stream. So we have the flow rate of the hot stream, Cp supply temperature, target temperature, and then we calculate the Q from that. So the amount of Q, the amount of heat, is also the same amount of heat is also transferred to the cooling water side, which is this. And then the last equality constraint is then the heat exchanger calculation. So we have Q equals to, in this case, U8 delta T LMTD. Yeah, we have the inlet outlet of the delta T LMTD. So this would be also equals to 0. So we have the equality constraint. And then the inequality constraints is about, so we have the supply temperature and then the cooling water. So the temperature in the shell, yeah, temperature in the water has to be greater than or equal to 0. So in this case, for example, so we have this is already greater to 0. Sorry. So we have here, this is 170, this is 80 degrees C, and then the cooling water is then from 25 to some number. So this is already more than 10, so this is okay, and this has to be at least 10 or bigger. Yeah. So this temperature can be maximum 160, 159, 158, 150, 140, and so on and so forth. So that this delta T is then at least 10. So that's what it means by this equality constraint. And another equality constraint is that all of these variables that have to be positive. Yeah, we don't want to have like minimum minus 10 ton per hour of water or minus 5 square meter of heat exchanger. That doesn't exist. So this whole thing is what we call inequality constraints, and the whole objective functions plus the 3 equality constraints plus 2 inequality constraints, they make the whole optimization model. As you can see, we have 3 equations in this case. Equations, yeah, equality equations 1, 2, 3. We have how many unknowns? We have all of this we know. All of this on the supply or on the process line, we know it. What we don't know is then the flow rate. We don't know of the water. The outlet temperature of the water we also don't know. And then the U we know. The area we don't know. The Q we also don't know. And so we have 1, 2, 3, 4 variables, unknown variables with three equality constraints, with 3 equations. That leaves us to 1 degrees of freedom. Yeah, so 4 variables minus 3 equations, we have 1 degrees of freedom. So you can see by manipulating this 1 degree of freedom, we can then calculate how much the other 3 variables, so that we can see how the objective functions is changing in regards to this 1 variable. So I have here with me, for example, so I have here with me, so we have same case. So we put all together some constant, yeah, any constant, and then in this case we use the outlet temperature of the water as our independent variable, as our degree of freedom. So based on this, we calculate the Q, and then we calculate the area and the temperature of the flow rate of the cooling water. Yeah, we vary this, and then we calculate all variables, and then in the end we also calculate the cost as the objective functions. So if you plot these two together, so we have the cost on the y-axis and then the outlet temperature of the water as the x-axis. So we can see it will vary from 160 as the maximum temperature allowed on the water to down to like 40 degrees C. For example, we can see that the cost is then reducing reduce until a certain point where it will by reducing the temperature further, we have an increase in the cost. We can see that if we reduce the temperature, that means we are going to use more and more fresh water. That means we will have if you can see here, if you go down from here from 160 to a lower temperature, you can see that the size of the heat exchanger is also lower because we increase the delta T LMTD. It means we increase the cost of the heat exchanger, but on the other hand, because we allow the temperature to be lower and lower, that means we have to put more flow rate. So the higher the flow rate will also be increase and increase. So we have like two conflicting cost functions, and then until a certain point where we have the minimum size of the heat exchanger due to the higher the LMTD, but we have a higher cost of the flow rate. So that makes this curve. Yeah, I think that that ends our today's session for the optimization model formulation.